Welcome to Saitechinfo channel. As part of the NEET chemistry lecture series, today I'll be explaining about surface chemistry. I already explained the topic tree, so you can refer my previous videos where I have discussed it in detail about the overview, the overall aspects about the surface chemistry. So today we'll be discussing the main aspects, that is main concepts like adsorption, catalysis, and then colloids. So all these three important topics will be discussed today. And this is one of the very important topics in chemistry where it covers variety of applications, variety of field. It is useful in chemical industries, in the manufacture of various mineral acids like sulfuric acid, and it is also used in the Haber's process of manufacture of ammonia. Then this is particularly this catalytic significance is very important in case of industrial applications. In drug industries, this is one of the very important that is topics. They are on day-to-day basis. They are developing variety of chemicals, variety of catalysts. So with the help of this catalyst, we are able to economically process the that is chemical manufacturing. Okay. So with this brief introduction, let me go into the topic adsorption. To start with adsorption. Adsorption is the surface phenomenon. It's a superficial phenomenon. Absorption means that is it is an interfacial phenomenon. It's a bulk phenomenon. When I say painting, it is an adsorption, that is coloring of matter on the surface only. Whereas when I dye, hair dye or any plastic dyeing, the coloring matter penetrates into the substrate. So that is the absorption. So add ADS, adsorption is the surface phenomenon. Absorption is the interfacial, that is bulk phenomenon. Okay, so you should make the difference between these two. Sometimes both may occur, and that is called sorption. Okay, so with this brief introduction, let me move further. Okay, so be ready with my lecture. Okay, so you will be having a lot of lecture notes. Kindly note down all those things. Okay, thank you. Saitechinfo channel. The series of NEET JEE chemistry lectures. Today we'll be discussing surface chemistry. In this topic, we'll be discussing the main three concepts: adsorption, catalysis, and colloids. At the outset, we'll be discussing about adsorption. So adsorption is a surface phenomenon. The molecules are adsorbed or adhered or attracted to the surface of a solid or liquid. It's an exothermic reaction, means heat is given out during adsorption. The heat of adsorption, that is, as I already mentioned, it is released during the adsorption. Now, we need to distinguish adsorbate from adsorbent. Adsorbent being a medium, it is a substrate on which molecules are adsorbed. Whereas adsorbate, these are the Adsorb the molecules over the surface of a solid or liquid. Balanced forces inside the substrate is very significant. So, but there are some unbalanced forces on the surface that is responsible for the attraction of molecules. And that is why a substance becomes, or a substrate or a material becomes an adsorbent, so that the finer particles or the absorbing molecules will be adhered over the adsorbent. In the case of adsorbate, there is a diffusion of adsorbate over the adsorbent. They will be spreading over the surface. For instance, let us consider charcoal. So this charcoal is an adsorbent, whereas acetic acid molecules, they are adsorbate. So these adsorbate, that is acetic acid molecules, can be trapped superficially, that is on the surface of charcoal. The solid or liquid can be an adsorbent, whereas gas or liquid may be adsorbate. Now let us discuss about the difference between adsorption and absorption. As I already mentioned, the adsorption is a surface phenomenon, whereas absorption is a bulk phenomenon. And the best example I would suggest is charcoal that absorbs the acetic acid molecules, whereas absorption, sponge absorbing water, that is absorption that goes into the what? The substrate. Then activated charcoal absorbs noble gases. In the case of absorption, sodium hydroxide absorbs moisture and CO2, that is carbon dioxide. Nickel absorbs a hydrogen gas in the manufacture of vanaspati, dalda, hydrogenated oil. So where nickel, the powdered nickel, the finely powdered nickel that is absorbed, that absorbs the hydrogen gas and that acts as a catalyst. Then turpentine oil, here it absorbs ozone. So in fact, sorption is the phenomenon where adsorption and absorption occur. Now we need to discuss about the physical and chemical adsorption. Physisorption, it can also be called physisorption. Physical adsorption is called physisorption. Chemical adsorption is known as chemisorption. So in the case of physical absorption, there is a weak van der Waals force of attraction between adsorbent and adsorbate. So the force of interaction between the adsorbent and adsorbate is very weak, is of physical nature. Whereas in the case of chemisorption, there is a strong chemical bond between adsorbent and adsorbate. Physisorption has low enthalpy, whereas chemisorption has high enthalpy. It has less activation energy in the case of physisorption. Activation energy is the energy required to activate, to react the reactants, whereas more activation energy is needed in the case of chemisorption. Physisorptions are not specific, whereas chemisorption is specific. That is specific on the nature of the substrate or nature of the material. There is an increase of physisorption with pressure, whereas in the case of chemisorption, it is not influenced much by pressure. It decreases with rise in temperature in the case of physisorption, whereas chemisorption increases with rise in temperature. Physisorption is a reversible equilibrium, whereas chemisorption is irreversible. In physisorption, normally multimolecular layers are formed at higher pressure. However, at lower pressure, unimolecular layer is formed. But in the case of chemisorption, it results into unimolecular layer. Adsorption of gas by solids. Here, there is a more adsorption in the case of, for instance, when surface area increases, adsorption also increases. And how can you increase the surface area? By powdering further, by making the powder very fine. So the finely divided powders or metals, they have more adsorption. Porous substances with a large surface area, they have more adsorption. So from this, one thing is clear: by decreasing the particle size of the adsorbent, we can increase the adsorption. It means by decreasing the particle size, we are increasing the surface area. Then, what is activation? It is the removal of impurities. We need to clean the surface of adsorption so that we support the adsorption activity, and that's why it's called activation. Then sometimes heating in vacuum or inert atmosphere, so that will improve. Then activated adsorbent has more adsorption capacity because it is activated, is it not? We used to say activated charcoal. Okay. Then adsorption of a gas by solids. This is a very important topic. See, here the nature of gas is one of the factors. Easily liquefiable gases generally are more readily absorbed. So gas with the higher critical temperature is easily liquefiable. Like in the case of hydrogen chloride gas, sulfur dioxide, carbon dioxide, ammonia. So these are all liquefiable. So they can be readily absorbed. So it means the nature of gas takes an important role. And then physical adsorption increases with pressure. Low temperature that always supports physical adsorption, whereas high temperature favors chemical adsorption. The Freundlich adsorption isotherm. X by m is directly proportional to P power 1 by n. So here X is the amount of gas adsorbed. Then m, that is the mass of adsorbent, that is the substrate where the adsorbing materials are adsorbed. So that ratio is directly proportional to 1 by nth power of the pressure of the gas. So when we remove the proportionality, you have to introduce the constant, and that is proportionality constant K. So when we plot the pressure in the x-axis and x by m in the y-axis, you are able to get a curve like this at constant temperature. So at 0 degree centigrade, at 273 Kelvin, you are getting a curve like this. With the increase of pressure, there is an increase of x by m, the amount of gas adsorbed over the given amount of adsorbent. Okay, but beyond that pressure, there is no further adsorption. It means there is a limitation. When we increase the temperature, decrease the temperature, now the extent of adsorption is more. When we further decrease the temperature, the extent of adsorption is much more. Are you able to understand this? Now, this x by m is equal to k into p power 1 by n. On introducing logarithm on both sides, we get log x by m is equal to log k plus log p power 1 by n. By applying the power rule of logarithm, you can bring this 1 by n to the coefficient of the logarithmic term. Therefore, log x by m is equal to log k plus 1 by n into log of p. Now, when we plot the log p in x-axis and the log of x by m in y-axis, now we are getting a straight line. Adsorption of the solution phase. In the case of solution phase, previously we discussed about the friend glitch where pressure is important. So in this case, being solution, concentration is important. So let me cite an example, the same thing, acetic acid solute particle adsorbed by charcoal. So with the increase of temperature, there is an increase of adsorption, and there is an increase of adsorption with the increase of surface area of the adsorbent. Then it depends on the adsorption, depends on the nature of the adsorbent and adsorbate also. We can apply this Freundlich adsorption as a term in solution phase also. So x by m, the same thing, amount of adsorbed molecules, m is the mass of the adsorbent. So this ratio is directly proportional to concentration. 1 by nth power of concentration. So x by m is equal to k into c power 1 by n, where k is a proportionality constant. Now let us introduce logarithm on both sides. Now we get log x by m is equal to log k plus 1 by n into log c, where c is the equilibrium concentration. That is, when adsorption is complete, what is the concentration at that stage? Okay, so that represents the concentration at equilibrium. Then there are some applications of adsorption. Production of a high vacuum. See, that is by introducing charcoal in a vacuum chamber. It further absorbs even the trace of air, and thereby you can increase the vacuum capacity also. So it produces high vacuum. Then it is also very effectively applied in gas mask, where the activated charcoal will be applied there in the mask and that absorb poisonous gases. So especially such kind of gas masks are used by miners, that is mine. In mine engineering, during the mining process, they are using gas masks. Then, and the control of humidity. Silica and alumina gel, they remove moisture. So by removing the moisture, we can control the humidity. Then solutions can be decolorized by incorporating animal charcoal. And there is a famous heterogeneous catalysis, and it is used in manufacture of ammonia using iron as catalyst, then manufacture of sulfuric acid. Heterogeneous means hetero means different. So this catalyst has different phase from the reactants so that it can be easily retrieved and removed. Let us look at this heterogeneous catalysis. As I already discussed, iron is a catalyst in the manufacture of ammonia by Haber's process. And then in contact process of manufacturing sulfuric acid, vanadium pentoxide is used as a catalyst. Let me explain about this contact process of manufacture of sulfuric acid. So actually, where this catalyst is used, this is used in the second step only. So actually, it consists of, that is the manufacture of sulfuric acid consists of three steps. Step 1, formation of sulfur dioxide from sulfur and oxygen. Step 2, sulfur dioxide is combined with oxygen to give sulfur trioxide, 2 moles of sulfur trioxide. In fact, its delta H value enthalpy is minus 196 kilojoule per mole. It means it is exothermic, whereas the reverse process is endothermic. So this is the equilibrium. Okay, so here it can take place only at a higher temperature. Okay, but at the same time, well, catalysts act at low temperature. But we have to choose in such a way it can withstand at higher temperature. So the powdered vanadium pentoxide that acts as a very good catalyst, and it can work in this temperature, and also the pressure is maintained at, from 1 to 2 atmosphere. So here vanadium pentoxide, the catalyst is very important, and also the temperature is 450 degree. Then third step, where by combining sulfur trioxide with water you can get sulfuric acid, but it's a very dangerous process, and that's why in industries they use sulfuric acid itself. They combine with the existing available sulfuric acid with the sulfur trioxide uptime, and they make it as a fuming sulfuric acid, H2S2O7. And then from this fuming sulfuric acid, further diluting, we can get sulfuric acid comfortably. Okay. Then further applications. Inert gases can be separated with the help of adsorption. In fact, the degree of adsorption of inert gases are different in charcoal. So based on the nature of the gas, it can be separated because the extent of adsorption will be different. So when you have got the mixture of inert gases, it can be easily separated because the extent of adsorption is different. Then curing diseases. Here, the drugs are adsorbed on germs, and thereby they kill germ. Then froth flotation process. So this is one of the wood processing procedures. Here, that is low-grade sulfide ore are separated from silica by using pine oil, by mixing pine oil and frothing agent, and they will be pumping air inside. So because of this frothing, so the gangue particles will be coming out. Thereby we can separate the low-grade sulfide ore from silica and other earth materials. Then adsorption indicators, they are used as absorption indicators, particularly silver halide precipitates. They adsorb eosin and fluorescent dyes so that we can find out the end point. So they act as endpoint indicator. Then chromatographic adsorption analysis. This is a great tool which is used in chemical industries and laboratory to analyze what are the elements present in a given sample. Let us discuss catalysis. Let me explain about catalysis. Catalyst, catalysis. Lysis means cleavage, cleavage of a chemical bond. Catalyst, using catalyst, we are breaking the bond. It means it is the reaction supported by the catalyst. Let us consider this KClO3, decomposition of KClO3. So this KClO3, normally KCl O3, KClO3 undergoes decomposition without catalyst. So about 653 Kelvin to 873 Kelvin at high temperature. It's when KClO3 is subjected to decomposition, it gives 2 moles of KCl and 3 moles of oxygen. So this is without catalyst. But at the same time, when it is decomposed in presence of manganese dioxide, a little bit only. We have to take very small quantity of manganese dioxide. Now the reaction is faster, and not only that, that is the reaction temperature has also come down to 473 Kelvin to 633 Kelvin. 633 Kelvin. Okay. So we get the same product. So 2 KCl plus 3 O2. So this is in absence of catalyst. In absence of catalyst, whereas this is in presence of catalyst. So in presence of catalyst, it is fast, and not only that, it reacts at low temperature comparatively. Whereas in absence of catalyst, that is, it is slow, and not only that, the temperature required is high, 653 to 873 Kelvin. So this indicates the importance of catalysts in any chemical reaction. So based on this, we can define catalysts. Okay. So catalysts is the substance which is added in small quantity. That is very important. Small quantity. Then it changes the rate of the reaction. It changes the rate of the reaction. It alters the rate of the reaction. Rate of chemical reaction. Chemical reaction. Thirdly, without undergoing any change by itself. So no change by itself. So that is also very important. Okay, it doesn't undergo any change, but it makes a change of rate of chemical reaction where it involves. Okay, and it reduces the energy of activation. Energy of activation. Now, this catalyst can be of two types. When we talk about the type of catalyst, we can have one is promoter, that supports, that enhances the reaction. Okay, sometimes it will affect the reaction also, so it can be a poison. Okay, it can be a poison. Now when the reaction is enhanced by a catalyst, that catalyst is called the accelerator. Sometimes it will affect the reaction, then it is called, it reduces the speed of the reaction, then you can call it inhibitor. Sometimes there are some substances which deactivates the catalytic activity, that is called poison. When it promotes further, then it's called a promoter. Okay. Let us consider the Haber's process of manufacture of ammonia. Of manufacture of ammonia, that is from nitrogen gas combining with a hydrogen gas, that gives ammonia 2NH3 gas. Actually, there is an equilibrium reaction, and here 3H2. Now, what we have to do? We have to take the iron catalysts, Fe, finely powdered iron, is taken as catalysts, and molybdenum, okay, molybdenum powder, molybdenum, that acts as the promoter for iron. Okay, so that acts as a promoter for this iron to activate further the production of ammonia. Catalysis can be broadly classified into catalysis can be broadly classified into homogeneous catalysis, homogeneous catalysis, heterogeneous catalysis. Homogeneous catalysis, heterogeneous catalysis. Homogeneous catalysis, the reactant and the catalysts, the reactant or reactants. So reactants and the catalyst are in same phase. Whereas heterogeneous is of different phase. Let us illustrate homogeneous catalysis with some reactions like sulfur dioxide, gaseous substance, on reaction with oxygen. It gives in presence of nitrogen oxide in the gaseous phase. So all are in gaseous phase. Are you able to understand this? So these are the reactants, and catalyst is also a gas. These are gaseous reactants. Catalyst is also a gaseous substance. And the product is also sulfur trioxide. That is also gas. So all are in gaseous phase. Gas, 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 gas. And that's why it is homogeneous. Do you understand? That is, they have same phase. And we can explain about the heterogeneous catalysis even in the liquid state. Okay, so let us consider another example. Let me consider acetate ester, hydrolysis of ester. Okay, acetic, as any acetate, methyl acetate, let us have CH3, COO, CH3. What do you call it? Methyl acetate. Okay, or methyl ethanoate. IUPAC name is methyl ethanoate. This is liquid form, and when it's subjected to hydrolysis, this is also liquid. In presence of hydrochloric acid, mineral acid, this is also liquid. Now we are able to get CH3 COOH plus, this is also an aqueous solution, and CH3OH, an aqueous solution. Got it? So all are in liquid medium only, and that is why it is homogeneous catalysis. Do you understand? And we can include another example. Let me take C12H22O11. What is that? Sugar solution, is it not? So this is also in liquid form, sugar solution as aqueous form. Okay, this is in aqueous form, aqueous solution of sugar. When it is subjected to hydrolysis, that is liquid, so it becomes in presence of sulfuric acid, that is also a liquid. Okay, now we get C6H12O6, that is glucose as aqueous solution, plus C6H12O6, that is fructose. So this is glucose, this is fructose. Both of them are aqueous. So all are in liquid state only. Therefore, this is also a very good example for homogeneous catalysis. So we have discussed point number 1, that is sulfur trioxide formation. Point number 2, that is it is a very good example for homogeneous catalysis, that is hydrolysis of ester, acidified hydrolysis, that is acid catalyst hydrolysis of ester. And third is, that is the sugar hydrolysis, hydrolysis of sugar into glucose. It may appear both of them are having same formula, but this is aldohexose, this is ketohexose. Okay, right. Now let us explain heterogeneous catalysis with an example like sulfur dioxide 2SO2 is a gaseous product. 2 moles of sulfur dioxide, that is converted into 2 moles of sulfur trioxide. Okay, so 2 moles of sulfur trioxide. So here the platinum acts as a catalyst, where you can find platinum is in solid state, whereas this is in gaseous state, and this also in gaseous state. Okay, so it means the platinum is distinct. The physical state of platinum is solid, and it is one of the advantages of using heterogeneous catalyst is it can be removed easily. Okay, next we can have another example also, like Haber's process of ammonia, as we already discussed. Nitrogen, hydrogen, this is gas, this is also gas, but here we have iron, that is the solid. Okay, so that makes the difference in physical state. So you get 2 moles of ammonia. Okay, so the physical state of iron is solid, the remaining are gas, and that's why it's called heterogeneous catalysts. Okay, so likewise we can give variety of examples. Let me write a chemical reaction. You have to identify as what type of catalysis. NH3 gas plus 5 moles of, this is 4 moles of NH3, this is 5 moles of oxygen as gas. In presence of platinum in solid form, we get 4 moles of nitrogen oxide as gas plus 6 moles of water as vapor. Now, what type of catalysis is? This is solid, whereas these are all gas, and therefore this is the heterogeneous catalysis. Okay. Let us take another example. Vegetable oils. You can take any vegetable oil. Vegetable oil, and being liquid, hydrogen is passed through this. Okay. In presence of finely divided nickel powder, we get vegetable ghee, that is called vanaspati, is it not? Dalda. It's in solid form. Now tell me what type it is. Once again, this is a heterogeneous catalysis. Okay. Why? Because nickel is solid and vegetable oil is liquid, hydrogen is gas. Let me explain about adsorption. This theory explains the mechanism of heterogeneous catalysis. Heat of adsorption utilized in enhancing the rate of the reaction. It is utilized in increasing, supporting the rate of the reaction. Therefore, adsorption is an exothermic reaction. Heat is given out. It has to be compensated. Heat is given out. Theory of heterogeneous catalysis. There are three important theories. Adsorption theory is one of the old theories. Intermediate formation theory. Then later came modern theory, that is a combination of adsorption theory and intermediate formation theory. Let us discuss this modern theory of heterogeneous catalysis. It consists of 5 important steps or stages. In the first stage, the reactants are diffused over the surface of the catalyst. That is number 1. 2. The reactant molecules get adsorbed on the surface of the catalyst. They get absorbed on the surface of the catalyst. And 3. Chemical reaction takes place on the surface of the catalyst through intermediate formation. There is an intermediate formation. So chemical reaction takes place. 4. Desorption, that is the removal of product. Okay, so desorption of a reaction. Desorption is opposite term to adsorption. So desorption of reaction product from the catalyst surface. So this makes the surface available again and again for more reaction. Then finally, such desorbed products should be diffused, is it not? So the diffusion takes place. So the reaction products diffuse away from the catalyst. Okay, so it is a continuous reaction. Now it supports very well that is the catalyst does not involve in the reaction, it just supports the or enhances the rate of the reaction. It means it describes about the retrievability of the catalysts. Okay, so that is one of the essential features of They are very good catalysts. Okay. Mechanism of heterogeneous catalysis. We have already discussed this. Our friend Akash has given a very good artwork in this. He has mentioned about the 5 stages. The first stage is diffusion of reacting molecules over the catalyst. Second stage is the adsorption of reacting molecules on the surface of the catalyst. So now it is getting adsorbed here. Do you understand this? A and B, these are the reactants, they get adsorbed. And because of the proximity of these two reactants, they are capable of reacting. So now they have formed an intermediate state after the chemical reaction. Okay, so this is the third stage. Then after the formation of this intermediate, now it should come out, is it not? So this AB is dissolved, that is removed from the catalyst surface as product here. Do you understand? Okay, and then it has to be completely diffused. Okay, so the diffusion of the product, so it should get away from that place, so that again a clean catalyst surface is available for further activity. Understand? So thank you, Akash, for your artwork. Now let me explain about the important features of a solid catalyst. See, we need to discuss the very important two aspects about solid catalysts. One is activity, another is selectivity. Activity means that is catalytic activity that depends on the strength of chemisorption, which is nothing but the chemical adsorption. Secondly, it should not get adsorbed strongly. Okay, so that is another type of requirement. If it is strongly adsorbed, being chemisorption a stronger force, then the adsorbed particles are immobilized. They cannot move here and there. That is, as they are strongly bound at one place. Then what will happen after the initial level of adsorption? There is no place for other reactants to interact with the catalyst. Let me consider this is the catalyst area, and see the molecules are bound here. Another molecule is bound with that is chemically it is absorbed. They are chemically absorbed. So chemisorption. Now what happens, since they are strongly bound, they cannot move. So that is called immobilization. Secondly, when they don't move, then how will it give place for the newcomers? Is it not? So that is the big problem. So no place for other reactants to interact with the catalysts. So such kind of reaction is exhibited by the hydrogenation in the case of group 4 to group 11 metals. For instance, hydrogen combines with oxygen in presence of platinum to give water. So this activity is more. This activity is more or the maximum in the elements occupying group 4 to group 9. Okay. So this is regarding the solid catalyst. Then selectivity. So selectivity is another aspect. It is that capacity, it is that ability to direct a reaction. to give a particular product. That's very important. So it means what? With different catalysts, with different catalysts, same set of reactants can form different products. Do you understand? For instance, let me illustrate with this set of chemical reaction. So here we have carbon monoxide gas, carbon monoxide gas, carbon monoxide gas. Similarly, hydrogen gas, hydrogen gas, hydrogen gas. So the reactants are same, but they form different products because of the different catalysts. Do you understand this? So it means they are very selective. When we use very fine powder of nickel, there happens the hydrogenation with more number of moles or molecules. Is it not? So it forms methane. We cannot expect the same methane formation by using copper or copper, zinc oxide, chromium oxide catalyst. Do you understand? So the reactants may be same, but they will give different products based on the nature of the catalyst. So that selectivity is something unique. Do you understand? I hope now you should be able to understand the solid about the characteristics features of solid catalysts like activity, okay, and selectivity. So these two are very important. Okay, right. Now let us move to the shape selective catalysis. Here we have zeolite. Zeolite is nothing but a microporous aluminosilicate with the 3D network of silicates. It will have a lot of pore. So this kind of catalysis depends on pore size of the catalyst. That is very important. Okay. And so this is with regard to the substrate of the catalyst, pore size. When it forms a honeycomb-like structure or cage-like structure, how about the porosity of that structure? What is the diameter of that pore? So these are all very important as far as catalyst is concerned. Secondly, the size of the reactant. So the size of the reactant and product molecules that should match with the pore size of the catalyst, is it not? So automatically there will be selectivity. Okay. So the shape selective catalyst, which is nothing but zeolite, is the best example. It's nothing but microporous aluminosilicate with three-dimensional network of silicates. And it has aluminum oxygen silica framework. It's a natural clay. So it has got the honeycomb-like structure, and we can synthesize nowadays the different types of zeolite. So one of the important synthesized one is ZSM5. That is used in petroleum industry. It is very specific. You please note down because it's very, very important for your fuel. With the help of this, alcohol is converted into petrol. Okay, that is by dehydration. You know alcohol or CH2OH. Okay, so you have OH. We'll say or CH2OH. So when dehydration takes place, automatically it forms lot of alkanes with various chains, is it not? So it may form a chain like butane, pentane, hexane, heptane. So here heptane, octane, nonane in that range. So you will be able to get kerosene. I'm not kerosene, petrol. So petrol, which is also called a gasoline. Okay, right. Now let us move with the enzyme catalysis. Enzyme is nothing but a biocatalyst. So it can also be called biochemical catalysis. So it's nothing but enzyme is nothing but a protein, that's all. So it's a complex nitrogenous organic compound. They are produced by living plants and animals. That is why they are called biocatalysts. So the objective of production or secretion of such kind of enzymes by the plants and animals is to maintain the life process, specific life process. As I already mentioned, enzymes are nothing but protein molecules. They are simply protein molecules, but maybe complicated. And they have higher molecular mass. They form colloidal solution in water. They obtained, they are nowadays obtained in pure crystalline form from living cells. The first enzyme synthesized was in 1969. Let us discuss some of the examples of some enzymes. Here you have invertase. Even the very name is given based on the activity of the particular enzyme involved in that reaction. For example, invertase. So that is responsible for inversion of cane sugar. Okay, so inversion of cane sugar. And let us discuss the examples, some of the examples of enzyme. We have invertase. That name is given because that catalyst is responsible, that enzyme is responsible for inversion of cane sugar, that is sucrose. So here we have explained inversion of cane sugar. Cane sugar is nothing but C12H22O11. Okay, that is nothing but sucrose, sugar, is it not? So on hydrolysis using the invertase, so they inverse, they optically rotate. In the optical rotation is inverted here. Okay, so that is why it is named as invertase. So that is present in yeast. Similarly, zymase. So yeast, that is also present in yeast, and this is responsible for conversion of glucose into ethyl alcohol and carbon dioxide. As I already mentioned, they are all very selective. Then diastase. Diastase, they break starch into maltose. It is a starch. Starch is a polysaccharide. You can observe here. So it is converted into, starch is converted into a maltose sugar. And then urease, that is available in soya bean. And this soya bean is, the urease present in soya bean, they specifically attack urea to give ammonia and carbon dioxide. You know the formula of urea, NH2CO NH2. Okay, so this decomposition of urea is achieved by this catalyst urease. Okay, so NH2CO NH2 becomes what? Ammonia and carbon dioxide. Okay, and pepsin, that is the enzyme present in stomach. So they are responsible for breaking proteins into amino acids. And in stomach particularly, you have, when you get, when you take any proteinous food containing protein, these peptides are obtained. That is, these are the hydrolyzed products of protein. Okay, polypeptide is called protein, is it not? So the proteins are broken into peptide, and in this is the case in enzyme. Stomach. That is pepsin enzyme converts protein into peptide. Then in intestine, the pancreatic trypsin converts a protein into amino acid by hydrolysis. it further breaks. Similarly, conversion of milk into curd, that is the enzyme called bacilli, lactobacilli. Lactobacilli means lacto means milk sugar. So lactobacilli enzyme that is responsible for breaking the milk, converting milk into curd. Okay, right. Then we need to discuss about the characteristics of some enzyme catalysis. They are most highly efficient. They are highly specific in nature. They are highly active under optimum temperature and optimum pH. They increase in activity in presence of activators, and they influence. There is an influence of inhibitor and poison in the case of enzyme. So these are the key points about the enzyme catalysis. Now we need to know something about the mechanism of enzyme catalysis. Okay? Yes. Uh, Pavani has drawn this diagram very well. Thank you, Pavani. So here, mechanism of enzyme catalysis. You can you are able to see the key-like structure here and a lock arrangement. So it's a kind of a key and lock. So here, this is we have the active site here. Are you able to see the active site here? Where on the substrate, that is the reactant, catalysts. Now the reactant, the substrate is reactant. On the site, this enzyme, okay, that is the catalyst, is capable of getting locked into the cavity, specially arranged, and there is a matching key. Okay, so that is why it is very selective. Selective. So E represents enzyme. So enzyme reacts on the surface of the substrate to give an intermediate. So this is the intermediate, and after that, after the entry, it breaks into pieces. See this? Now we are able to get, now the enzyme is retrieved. You can take back the enzyme and you have the product now. Are you able to follow? So in such a way, biologically, it can break into new product. Okay. So it's a kind of lock and key mechanism. So they possess active groups like amino group, carboxylic acid group, and TO alcohol group. OH means alcohol, SH means TO alcohol, then S means TO sulfur, then OH alcoholic group. They have characteristic shape, so as I already mentioned. Okay, and in the colloidal particle they have larger number of cavities present like this so that it can get into the lock. The active centers on the surface of enzyme particles, okay, the active centers, it directly enters there. Substrate is the reactant molecule, and they have the complementary shape as I already mentioned with the cavities, and that accommodate an enzyme. Specifically, it can accommodate a particular enzyme only. It cannot take all. Okay. So that is why it is highly specific and selective.